So these are my co-authors, somebody you know, and people working on the brain. So this is the problem I'm interested in. How does this mess of neurons, synapses, molecules, genes, and so on gives rise to cognition, behavior, intelligence, language, the good things. In fact, I'm so interested in this question that I call it the sunset or the Golden Gate Bridge question, in the following sense that whenever I see this, what comes to my mind is, why doesn't everybody stop what they're doing and come here to see this? Okay, so that's the mood I'm in when I work on the brain. Okay, why is anybody working on something else? Okay, so being a computer scientist, I have put my money on the eventuality that when we know the answer, it will be at least to a good part computational. And as a result, computer scientists should work on it. But it's easier said than done. Okay, so I've been trying for 3.5 years. Okay, so and it's not easy. So the question is, how does one think computational about the brain? So this is an old question. Turing, for example, used the brain as inspiration for his Turing machine, as also as a challenge for his computers. For Neumann, just a couple of years before he died, he wrote a fantastic book that was published, Computers and the Brain, posthumously, and among a lot of humblingly brilliant insights he has about the brain and computers, by the way, he said this, which is, I think, an amazing insight, that the way the brain works may be characterized by less logical and arithmetical depth than we are normally used to. Okay, so it says, don't expect too much algorithmic sophistication. Les Valiant has been working on the brain for 25 years. And in the 90s, he published a brilliant book called Circuits of the Mind. And he also proposed the model for algorithmic model of the brain. And I'm not going to tell you the important ways in which what we do differs from Les's model. But I'm going to quote him on this, that the computational theory of the brain is both possible and essential, okay? Which I totally agree and respect. Fine. So this man taught us how to think computational about the brain. Okay, so he's a Turing-like figure. He was my colleague at MIT when he died at the age of 35, and he wrote. The decade before, he had written the most amazing 3 thick papers about the brain. And just before he died, he articulated a methodology which is respected to the day, and I'm following. Basically, in order to understand how a system in the brain works, you have to do 3 things. First of all, understand the specs. Okay, I'm changing the nomenclature because it has changed the last 40 years, but he meant specs. The input-output behavior, what the thing does. Okay, and this you get from neuroscience experiments and cognitive science experiments. Then you have to find the hardware. In other words, what cells, what genes, what molecules are implicated in this work. And then you have to find the algorithm, the process whereby this hardware is put together in order to affect the specs. So the question is, can you use Mars framework to identify the algorithm run by the brain? Okay, and what's your pick? Okay, so we have all these choices. So, what's your favorite algorithm? What do you want? What do you think the answer is? Okay, no. We shouldn't, okay? So here's what I think we should do. We should do what Valiant tells us to do, computational theories and models but we should make sure that they are consistent as much as possible with what we know from experimental neuroscience, okay? And experimental cognitive science, I should say. And start by accepting defeat. Expect expect that there's going to be 10,000 algorithms to describe, to discover, and we should be ready for the long haul of finding them one by one. Okay? And that they're going to be disappointing. Okay? They will barely deserve the name of algorithm. Okay? As von Neumann said. Good. And I propose that we begin at a relatively safe place, which is long-term memory. So let me tell you an interesting experiment. Okay? Came out a couple of years ago. So they recorded from one neuron in one patient. Okay? Actually, they recorded from a dozen patients and several dozen neurons on each, but let's focus on one neuron and one person. So they were showing them about 100 pictures, 100 to 100 pictures. For example, they show them this particular neuron specializes on Eiffel Tower. Every time they show them the Eiffel Tower, the neuron fires, okay? You show it the Forbidden City, nothing, okay? You show him Eiffel Tower, fires. You show him, he was our president, okay, remember? Now, you saw him Obama, boy, I miss this guy. I don't interject political messages in what I say, okay? No, but I want to remind you one thing. Einstein said that the world is a dangerous place, not because there is evil, but because good folks do nothing, okay? So here's my point. If you see evil in the world, don't get caught doing nothing. All right, so, on lighter subjects, okay? So then they do the following, okay? They Photoshop Obama in front of the Eiffel Tower. They probably do it in a more able way than I did, okay? So, and of course, the neuron obliges, okay? So, it sees the Eiffel Tower, fires. Then they show him again the Eiffel Tower, of course it fires. They show him the Forbidden City, nothing. They show him Obama. The neuron fires. Get it? My eyes get watery when I tell you this. This guy has learned that Obama has been to the Eiffel Tower, and you discover this experimentally. Okay, I think this is very remarkable. So, in short, these are the specs. What is the hardware? What is the algorithm? This is what I'm going to work on. Okay. Let's speculate about the hardware first. Okay, let's do some back of the envelope. They recorded for about 100 neurons out of possible, 20 million neurons in this subject, and they showed him about 200 pictures of familiar person places, okay, with repetitions. And they only had 5 or 6 hits, okay? What does this tell you? Sorry. They had about 5 or 6 hits. This tells me that every one of these memories, because these memories were there, every one of these memories is represented by about 30,000 neurons. Okay, so the Eiffel Tower, we chanced upon it, but it's one of maybe 10,000 neurons that represent the Eiffel Tower. And in fact, that's not a new idea. That's an idea that's an old idea whose time has come. So because already in 49, Hebb was telling us this, and now it's sort of the putative way that we believe that memories are represented in the brain. And Valiant had a similar, but sort of, again, significantly different idea in his book. These assemblies, as they're called, are highly connected and therefore stable. An assembly is formed by, so when you see the Eiffel Tower for the first time, maybe at the third time, you decide, okay, I have to remember this, okay? And then some attention mechanisms creates this memory trace. Every time we think of the Eiffel Tower, approximately all of these neurons fire. And then Obama and Eiffel Tower can be associated by creeping somehow into each other, okay? So this is what I think, all right? I mean, this is, of course, has to be speculation. Or may have to make falsifiable hypotheses here. This is the job of a theoretician. So the question is, how are assemblies formed and how does association happen? This is what the algorithm part. And the point is that we are asked to solve an impossible problem. In a sparse random network, how can you select a densely connected subnetwork? This is a problem that we have learned to, this is reminiscent of a problem that we have learned to respect and avoid. Okay, so how are we going to solve this? So let's make a hypothesis, okay? What I think happens is that when we want to remember the Eiffel Tower, this thing in the visual cortex fires, spikes repeatedly, and this creates an assembly over there. Okay, that's what I think. I also think that when, by the way, when I write a circle like that, I mean that these things are scattered. Okay, but I represent it by this way. And when Obama and Eiffel are spiking together, are presented together, then these things come closer. All right. I mean, so the question is, how are we going to prove this? Okay. So and here is a model that we use. You have two large set of vertices, a huge graph, two large set of vertices, the sensory cortex and the MTL, medial temporal lobe. That's where these assemblies live. It's around the hippocampus. The synapses, the directed edges from the temporal for the sensory cortex to MTL and from the MTL to itself, they form a GNP directed graph. With discrete time, it's not, most of these, almost all of these, we can relax and with harder math. But let's stick to that. Initially, all synaptic weights are 1. And then a set of K neurons encoding the stimulus in the sensory cortex, the Eiffel Tower, fire for T steps. That's the presentation of the stimulus. And at each step, we assume, so what is our model, how do neurons respond? And what we assume, and that's also controversial, but we can defend it and fix it. The K neurons in MTL that have the largest synaptic input combined from the sensory cortex or from recurrently from MTL, these K neurons that get the most input, only those fire. Okay, so somehow, you get a couple of, and we also assume plasticity. That's very important. Okay, because plasticity is how we learn. Okay, so that we know modification of from experience. If at time t cell I fires, and at time t+1 cell j fires, then the weight of the synapse ij, if it exists, increases by a small amount. Okay, this is sort of a modest, simple model of plasticity. Okay. So what we can prove? I'm going to go quickly because we can prove quite a bit more, but this is that the set A sub t of currently firing MTL cells will rapidly converge to a limit A. And this limit will consist of some cells that get a lot of synaptic input from the stimulus, we call them born-rich, some hybrid cells, which are the ones that fire in the second step because they got a lot of input from A1, and a small number of late recruits, and these late recruits exponentially decrease as time goes by. It will be quite highly connected, and if the stimulus is presented again, all of A will fire. But all this, of course, with high probability. Okay, because that's a randomized algorithm. Also, after the sequence of presentation, first Eiffel, then Obama, then Eiffel and Obama together, then Eiffel, then Obama, a small but not vanishing cells in the Eiffel assembly will also respond to Obama, and vice versa. Okay? And we chanced upon one such cell, okay? This is what happened in this experiment, okay? We found one of these few cells that move. Okay, in fact, it turns out stronger results we get if we assume an enhanced model which we call GNP++. Here's what the enhanced model says. And basically, it's based on the results that first were discovered by Song et al. In an experimental paper, and then were verified and repeated in many other contexts. So basically, the point is that the chance that there's an edge from here to there is, let's say, 1%. But once this edge exists, condition on this edge existing, the reciprocal edge exists with very much higher probability, let's say 1 in 10. And similarly here, the chance of each one of these edges is 1%, but if they both exist, then this becomes extremely likely, okay? This is called triangular completion and reciprocity, and they sort of completely change, and one of the most important questions I think, I should tell you now, in my mind, is one of the most important hypotheses that come out of this work is, are such combinatorial completion biases an integral part of the way the brain works, okay? Or are they accidental, okay? So, or are they, yeah, okay. Okay, and the reason they work is because if you take two cells in the assembly for Eiffel, okay, that's created by that, a birthday paradox is at work, okay? And these are very likely, so they're not quite random cells over there, right? I mean, there is quite likely that they have a common ancestor, and therefore they have increased chance of being connected, okay? In any event. And now let me tell you about the Greek challenge, all right? I mean, how do you find a well-connected graph in GMP, okay? I asked people who should know, okay? I asked people who work on graphs, all right? I mean, I teach algorithms, right? I mean, so I asked Aviad, they gave me a few ideas, and the brain does better. Okay, so here's what I call the brain's algorithm. It's a stretch, both because it's a hypothesis, and because it's extremely stylized version of what happens. Okay, but here's how the brain does it. You pick a random set of alpha k vertices. Okay, random. You find 1 minus alpha k vertices with the most edges from those. You put them together. And that's your set. And then you optimize alpha. Okay? And if you have plasticity, a B++ and birthday paradox, you do even better. Okay? These are things that are not accessible to algorithms, but the brain can do them. Okay? Okay. So how much time do I have? By the way, 2 minutes. There are many questions here. Okay, so if his watch beeps, okay, you know what question to ask in the question period, right? I mean, I'm joking. Okay. So I think that this is relevant to language, okay, which is basically what I want to work on. Linguists think that we make and comprehend language by creating syntax trees, okay? The assembly formation mechanism, I think is relevant for this, okay? The mechanism that I presented, okay? And you may ask, do you really think that when we talk, we build trees in our brain? Okay, so this sounds sort of incredible, but I do think so, okay? And I have prepared for you sort of, but I'm going to skip it, some incredible experimental results that convinced me that yes, we create when we produce and when we comprehend language, we do create trees. Okay, and if you believe that, and in fact, I mean, also I'll tell you this experimental fact, which is amazing. I think this is where this is MTL. This is where I think the lexicon resides. This is where the lexicon is projected, I think, as a workspace to create trees. And this is Broca's area. This is this is where the internal nodes of the trees are created. Okay, I think. In any event, so here is an amazing experimental fact, that these pathways, these sort of neural superhighways that connect this area with Broca's area, and basically they're the pathways that create syntax, they found out that they are myelinated, which means they are sort of given for use, public use, near the second year of the baby's life, exactly when syntax kicks in, exactly when the baby has enough lexicon and starts understanding sentences. Okay. In any event, in order for such a hypothesis to be solid, you need a repertoire of assembly connectors, and of course this we have. This we are working on, and this we are working on. Okay, so fine. So to conclude, how does one think computational about the brain? I think that this, that this path is okay, seems viable. MAR, okay, so experimental neuroscience and cognitive science provide the specs and the hardware. As von Neumann eerily predicted, the algorithm vanishes. Okay, so it becomes sort of like a simple, repetitive, sort of an empty loop. And in some sense, the algorithm is reduced to much more subtle and implicit algorithmic elements, like setting parameters, creating the architectural development. Okay, that's an amazing algorithm. Biology, evolution, another algorithm, plus extremely simple algorithms, online algorithms. Okay, and ultimately, I want to go to language. Okay, so thank you very much.
Your paper is talking about the algorithms by which engines form. There's a completely distinct level at which algorithms operate in the brain, namely the processing that's then done during the interrelated pattern of firings that's resulting from the connections that we've learned.
You mean,
So
you mean things like deduction?
Processing in the moment. Yeah.
Right.
Okay. Yeah. Deduction. Or getting from low-level visual inputs into recognizing that I'm one of the
Yeah.
So, do you predict that those algorithms also are very simple?
Yeah. Okay. I grab on the second part of your question, right? Which is low-level vision and so on. As you saw, I started right after sensory. Okay, a lot of algorithmic work has gone into sensory, and I think that I deliberately chose to start where sensory, the sensory cortex, auditory, olfactory, visual, is intimately connected with the world, okay? With outside world, okay? Sort of, the representations reflect the world, okay? There are edges, there are colors, there are motions. The MTL is the first time where it becomes abstract, okay? You have a projection and you have an assembly, and that's abstract, okay? The connection to the outside world have been severed, okay? And that's where it becomes symbolic, okay? That's where symbolic intelligence starts, okay? And I think that this is a neat place to start thinking about the brain for us. Yeah?
So, about CMP and stuff, do you think that this speed could change with time or?
This peak? Oh, yeah. So P is, okay, change with time. So one thing, okay. we talk about algorithms for the brain, right? I mean, so we should be a little humble. What happens in the brain is going to be much more messy, chaotic, wet, grungy. But the point is that if you can say in a clean way what you think might happen, okay, and the brain is able of doing it, maybe this is the principle that underlines all this chaos, okay? Maybe, so, that's what we are trying to discover. We are not going to discover in any, so P, P doesn't exist. P varies tremendously from region to region, okay? So, the edges come and go, okay? So, synapses come and go, right? So, nothing that, they do also in computers, but sort of, but for some reason, sort of, we are forgiven to ignore it. But here, sort of, you are reminded all the time that all of this is P, for example, okay, sort of, is something that I used in order to have a theorem, so so that my paper can get into ITCS, okay? So it's not something that I believe that it has an objective reality in the brain. So it's more yeah, it's going to be much messier.